Elchanan is the founder of Logic and has 35 years of experience in both design and verification. For the last 15 years, he has focused on high-end formal verification projects and is a regular speaker at formal conferences and events. His formal verification clients include ARM, Microsoft, Mobileye, Texas Instruments, and Intel. Okay, and the title of the presentation is Porting and Verifying a Pre-RTL Legacy Design. So over to you, Elchanan.
Okay, great. So thank you very much. I'm Elchanan Rappaport from Logic, but I'm not so particular about that. Okay, there's nothing new on this slide that wasn't just said already, so that's a little bit of who I am. Let me dive right into our customer predicament. Our customer had this mobile communication system which they sold, however many of them that they sold when they came out with the system 20 plus years ago. And they were fortunate enough to have a large order come in now, just as we're speaking pretty much about now, several months ago, I'd say, for a whole bunch more of them. Unfortunately for them, the system is built around an FPGA device, which has been end of life for quite a while. And even their design database, their design methodology is not really compatible with current FPGA devices. So you see the graphics, they're kind of like the dinosaurs. They know the meteor is coming, but there's not really much they can do about it. So rather than just give up, they came to us with their challenge. Their challenge was that they had a pre-RTL legacy FPGA design, no RTL. It was ViewLogic schematics, buggy EDF netlist, and by buggy netlist I don't mean a design with bugs represented in EDF. I mean there were bugs too. I mean that the EDF netlist had bugs in the way it presented the design, and design was horribly asynchronous. I'll get to that in a minute. And our challenge, what they wanted from us, was to create RTL which was synthesizable to current FPGAs. To make it synchronous, and that's a goal because due to lack of clocks and other things, we couldn't make it 100%, but to the extent we could. It had to be a cycle accurate match to the original. This is a legacy project. No one around really understood it that much anymore. And they could, anything that we did that was even one clock different from the current design, we didn't know if that would fit into the system. It's kind of like walking through a minefield. You exactly retrace the steps of the person walking in front of you, because if you step out of their steps, you don't know what you're going to hit. So that was how we had to recreate the design. As far as verification, there wasn't really any. There was no simulation desk bench. There wasn't even a detailed functional description. There was just take it as it is and good luck. Some of the projects and talks you've heard here, I'm sure, are cutting-edge designs using cutting-edge tools and apps. This is not one of those. This was one where you just kind of look up to the heavens and say, please help me get out of this mess. So that's where we are. I mentioned the design was asynchronous. Things like ripple counters, where the output of one stage flip-flop feeds the clock of the next stage, which is similar to ripple counters. Where the clocks that were being fed into flops were some combinatorial product of different clocks and non-clocks being ORed together. Functional resetting of flops to the async reset pin, as opposed to anything that's coming into the clock or enable or data lines. A real mess. So let me describe, on all my runs of this talk, I run overtime, so I'm trying to say less and possibly run short, so you'll ask me questions at the end if I skip anything. So we basically had three design inputs. One was the ViewLogic schematics, which I mentioned. They are not machine readable. Basically, it's a PDF file, which you can print. I was kind of amazed they even had PDF files, but I was grateful for them. And these go down to, in addition to simple primitives like ORs and flops, to some higher level primitives like this 4-bit counter you see here. And a little bit of, how I know it's a 4-bit counter. So that's the first input, non-machine readable. The second input, which was machine, and I'll go back for a second, non-machine readable, but somewhat understandable to the human eye. The next input was machine readable but less human understandable. These were the buggy EDIF net lists, which went all the way down to the low-level prims, meaning you didn't have to deal with a prim stopping at a counter. It went all the way down to the flops and ands and ors, okay? But there are a lot of inconsistencies and things wrong with these files. There were missing or incorrect port directions. There was a lot of renaming, which is inconsistent. All sorts of other kludgy artifacts. And it could not be fed into any, even if we were willing to say, okay, we'll use a net list as opposed to RTL, even if we're willing to stay asynchronous as opposed to trying to clean it up, this could not be fed into any usable FPGA tool. So we couldn't work directly from it. Our third input, and this is bless their hearts, the FPGA vendor, way back when, they probably sensed that the methodology they had would not last forever, provided in complete detail descriptions, block diagrams, truth tables of all of the primitives. So I was able to use this as a Rosetta Stone in understanding what was actually contained in the design once I got down to the primitives. Knowing the difference between this a CD4RE and the CD4SC matters because you can't just infer that from the view logic. Okay, so here's the process which, this is basically what we implemented. This is how we did the project. Oh, I think I get a cursor here. I get a spotlight, yes, okay. So first, the blue path above is generating our reference net list. We have the EDIF net list, which I made reference to. I wrote a Perl script. I write really ugly Perl, but it gets the work done. To translate it to a Verilog netlist, but also repair, infer directions, infer structure. It had a lot of, I'd say smartness, but that would be giving too much credit. It had a lot of hard-earned, sweat-developed heuristics in order to be able to make something comprehensible out of the EDIF. And that gets fit into our reference net list. We also took our Rosetta Stone for the low-level primitives. We didn't have to deal with the counters or higher things because the EDIF went all the way down to low level. For flops and ands and ors and the like. They actually end up tens of primitives, but they were all rather simple low-level ones, and just manually code them as Verilog, which wasn't too hard. You know, the longest of them was 5 lines of Verilog. It was not much. And those two taken together are our reference net list. Now, the reason that it doesn't stop here and we feed back around is because it was an iterative process. The Perl basically took what it had, generated a Verilog dump, and hopefully that was good enough. So even though we didn't have any simulation environment to exercise the design, just being able to compile it in the simulator was able to point out to us missing declarations or things not connected or things that we need to deal with. Similarly, we built it onto an FPGA, synthesized place and route tool to see if there were any errors there that the FPGA tool complained about. And again, and any errors there, or even warnings there, we fed back around, fixed up the Perl, and after enough iterations, we had what I consider to be a reasonable net list. Although it's asynchronous and had other problems to it, functionally it was a solid reference. The green path is generating our new RTL code, which eventually goes ahead to become the customer's design. We had the view logic schematics, which are not machine readable, just we went through them, just kind of across each page of the schematic, just going left to right, implementing one block after the other in VHDL, along with our Rosetta Stone. So we came across a counter, we would see the exact functionality of that counter and write that counter's function in VHDL. Those two taken together become our RTL design, which we go off and build the FPGA and send it to the lab. Now, the orange here is actually what I'm going to talk, most of this talk is going to be about, which is how we established equivalence, correct functionality, that our design, in fact, correctly represented what the original one did. And the reason that it's not, that it feeds back to here, not just here, is because as we were going ahead left to right, developing gate by gate, line by line of VHDL, I didn't wait until I got to design outputs. On all the intermediate internal signals, or the ones I thought would be of relevance, I went ahead and I executed equivalence checking to see if I was still on track with the original design. And again, this was a very iterative process. Write a few lines, check, write a few lines, check, till eventually we got here. At this point, we just checked the outputs of both FPGAs, of the netlist versus the RTL, to see that they matched. And we kind of put through aside all this intermediate results, because obviously if the outputs match, that's one of the beauties of formal, that if your higher level output matches, that's a complete match. You don't have to worry that you missed some other details in some inner interface. Okay, so here's our methodology. Let's talk about the orange part a bit. Sorry. Ooh. I've lost the ability to page down. Do I need to shut this off? There we go. So I'm getting up on that cursor. It had a little gotcha to it. Okay, so our design blocks fell into two basic categories. One is clock dividers, tone generators, which can be characterized by having very few inputs, easy to infer functionality, very long sequence lengths. And for those, we use the equivalence method of just simulating them, because we could, and it was easy. Everything else, which was the majority of the design, did not fit into that nice profile. They had a large number of inputs. We had no idea whatsoever what the functionality was. The sequence lengths were, I'll say, short to mid. And mid, I'm taking liberty, is what's meant by mid. And for those, we use formal. Okay, so how did I use simulation equivalence? This is the easy part. I just create a simple test bench to exercise all the modes. Remember, there aren't that many inputs, so there aren't that many modes. And on every cycle, I just exhaustively compared my RTL. In this example, my clock divided by 4 in the RTL versus the clock divided by 4 in the netlist. And if it mismatched, pull the plug on simulation and pass the check. After I did this, I went ahead and, since I established that those blocks were the same, I replaced the original blocks with my more cleanly written VHDL RTL blocks into the comparison. I didn't see reason in making the formal tool struggle harder on poorly written code when they already established through simulation that they were identical. Okay, so formal equivalence. What type of formal equivalence is there? There's the original formal equivalence, which we've known for decades, which you use to check your synthesis worked well, which expects a one-to-one mapping of the flops and the combinatorial logic to be exactly the same at all points. More recently, it's been a while already, we have sequential equivalence checking, which is able to deal with implementations which are dissimilar but still provide the same outputs. And here, instead of manually having to write anything, you just have the tool will infer for you assertions on all of the outputs that the RTL and the outlet outputs are identical to the netlist outputs. Another way of using pretty much the same engines, but a different interface, is using standard system Verilog assertions and writing them. Again, it's okay to have similar implementation. And you need to manually create properties for all of your relevant outputs. Sig1, netlist Sig1 is equal to RTL Sig1. An advantage of using this method, of using this entry, I'll say, is that it's easy using system Verilog assertions to add additional constraints, meaning environment constraints that you know you're never going to get a write strobe and a read strobe at the same time, or to do conditional testing. Let's say the way you've implemented your newer design, you don't deal with invalid states because it's more efficient. But the tool will find that in the case of invalid states, you mismatch. So you can tell it, I know I'm never going to invalid state. Maybe you're going to check that separately. And when it performs this equivalence testing, don't bother checking for invalid states. Okay. Now, this slide, I'm going to have to say carefully so I don't get myself into trouble with anyone. Formal tools are essentially designed to deal with synchronous designs. Now, the manually created RTL we have is generally synchronous. Not as perfect as I would like to be, but generally synchronous. Our reference net list, which the formal tool also has to deal with because it's comparing one to the other, isn't even close. It is terribly, horribly, and in a very ugly manner, not synchronous. Now, there is no shame in formal tools not being able to handle asynchronous net lists. They weren't designed for it. And it's not a negative reflection on any tool that can't. Having said that, after trial and error, only one of the formal tools which I had access to was actually robust enough to be able to deal with my created net list, which wasn't a surprise, as well as the garbagey asynchronous reference net list, which was OneSpin. You can tell by the logos there. And I am very grateful to them that they had a tool which was capable of doing it, but the other tools are really wonderful tools and really work well, and I can't fault them for not being able to do what they weren't designed for in the first place. Okay, so there were actually in this project 5 different FPGAs, 2 basic different types, and a few variations. Not giant FPGAs. You see here the number of outputs for each one. SimProps is the number of properties, and I've got properties for each output that they match between the netlist and the RTL. Here's the number of properties I was able to deal with simulation. You see they're a relatively small percentage. And the rest are formal properties. Mismatches, I just throw the tool at it saying, okay, show me that all the outputs are the same. And you see that the majority of them fail. For the 3 on the left, it's the overwhelming majority. For the 2 on the right, it's still more than half. Which doesn't mean that our designs are completely dissimilar in terms of the outputs. Well, it does. It means that somewhere along that cone of influence, there was some signal who was different, and that projected to the output. Okay, so I went ahead and looked at the counter examples and see what are we dealing with. Here's a typical example of what caused our problem. In the blue above, we have the original implementation of, these are bus registers. These are registers that are written from a CPU bus and then used internally in the FPGA or sent elsewhere. So coming in from the left-hand side on the top blue, you've got the bus address coming from the CPU, compare it to a fixed register address. And if the address matches, we go ahead and invert it so it's active low. We AND that active low address match with the active low right strobe and the active low chip select. And that generates the clock to the flop, at which point it clocks in the bus data. This was the original netlist implementation. Looking at this and thinking of putting it in my logic that I was writing, the idea of so many signals combinatorially being combined to generate a clock is just kind of, I'm not quite sure. I might have Hebrew words for it. I'm not sure what the English word they use for it is. So the cleaner implementation in green below is I compare the bus address, positive logic, but that doesn't matter. I take my chip select, I invert it so it's positive logic also. By the way, the handouts, the printed handouts you've got have a few typos in them, such as not having the inverter on that chip select there. So I apologize for that. There are probably a few other spelling typos also. And the result of that AND becomes the enable, and the clock to this flop is the is the trailing positive edge of the right strobe. And this is it's synchronous. It's not based on a free running clock, so you might call it asynchronous, but in terms of the cleanness of the design, this is a clean signal coming into a flop. So I went ahead and applied. As I said, we don't have any functional description of this FPGA. But what we do have is a data sheet of the microcontroller that it's connected to. So I felt comfortable in adding the. Oh, I jumped ahead of myself. This is a failure. This is the counterexample that shows why these two aren't the same. You see that in the original blue design, a rising edge on chip select will also cause a rising edge on the clock and clock in data, which is what happened. Whereas in my green design below, a rising edge on chip select will just affect the enable, but it won't clock in anything. So this was a miscompare. This is a screen capture from OneSpin, obviously, if you're familiar with it. So now I went ahead, I looked at the CPU data sheet, and I had the limits that you can have read and write strobes together, that chip select is an envelope around the right strobe, and that the data and address are stable during the right strobe. And with this, I was able to confirm that they matched. This is a cover trace because I didn't get a counterexample because it passed. So going ahead and implementing those CPU restrictions to make it constant CPU, I reran my properties and was left with only a very small number, relatively, of failing properties, the bottom row here. So let's try to understand where that came from. Okay, so here is a counterexample. Took 431 cycles to get there. This functionality here is basically a UART, an RS-232 type UART, where the CPU writes data, strobes, and says, okay, go send it out, and the FPGA chunks out the serial data at its own much slower clock. And the tool found a miscompare. And the source for this miscompare is that as you see, there's a line called UART trigger. The top trace is fully zoomed out. The bottom trace is zoomed in enough to see what happens at the end where there's a miscompare. Sorry if that wasn't clear. You see the UART trigger signal happens, and that exercises the difference between the netlist and the synchronous implementation. So I had to go back and talk to the who I could find of the software of the embedded team of the customer and confirm that they would never actually send out another trigger while the previous one was being sent out. And I added that as a constraint. And sure enough, that dealt with all of the miscompares. No miscompares left, meaning that other than what I've presented above, what I've said so far, I had no other functional understanding or no other constraints as far as the environment. Meaning this methodology worked in the absence of any functional knowledge of anything. And I was still able to actually perform a full verification that our design matched the original design. And like back to the example, walking through the minefield, didn't step any place that the original design going through the minefield didn't step. Okay, here's an example of something we came across the way. When something seems too good to be true, it probably is. I mentioned as I was going left to right, developing the blocks, the code one by one, I came across a signal which matched even before I implemented it. And it also matched like right away as opposed to chunking for a number of cycles or a certain amount of CPU time. So I looked what we had, and what you see here, this is a race condition in the original design. There's a counter whose most significant bit clocks the next counter, but that same bit, the same most significant bit, comes around and resets the original counter. So you've got a race. Does the rising edge of the most significant bit clock the next counter before he gets cut down by his own reset? Now, when the formal tool looked at it, it said, oh, even in the original netlist, the second counter can never get exercised because there's just a glitch there. There's no real signal to clock anything. So it said the original design was 0 because of the race. My new design was 0 because I didn't implement anything. So it matches, which is why you need to be aware of what you're doing a little bit. And I added for all of my outputs cover 0, cover 1 properties, sort of equivalent to vacuity in regular SVA properties. And there were a few which, in fact, were only 0 or 1, but I checked the code, and those were hard-coded, intentional, fixed-value outputs. But otherwise, all the outputs had to pass this test that they were also hit 0 and 1. In the real world, this actually went to the lab, and this actually worked. There were only 2 bugs that they found in the lab, and I was given the level of challenge, I was rather proud of that. One was looking at the data sheet and the board design, we understood our repetitive clock, our free-running clock, to be well distanced from our right strobe. And in fact, in the lab, it turns out that they were completely coincident. You see the rising edge of the blue free running clock falls exactly on the edge of the right strobe. And that's set up hold and violations. And in the real world, those things really mean something, and it didn't work. So we had to adjust our logic to key off of the negative edge of the free running clock rather than the positive edge, and that solved that problem. There was also another missed race condition. I showed you above the example of race condition where it just was so egregious that it didn't even exercise the logic at all. Well, this was a more subtle race condition, which we didn't pick up and was picked up in the lab. So for this block, for this small sub-block, we actually had to go ahead and rewrite it from scratch and use the original FPGA's timing captured on a scope in the lab to tell us what timing we need to generate, which was rather painful, and it's good that we only had to do it for one small block. Conclusion. So in the earlier slides, I presented the dinosaur with the meteor coming at it. Actually, there were two dinosaurs, a little baby one if you were paying attention to. And what we did here is we still ended up with something terribly ugly, but we taught the dinosaur to fly. As I said, this was an example of cutting-edge tools, an example of competent tools, robust tools. Certainly not a cutting-edge design. This is a design from the Stone Ages where they use Stone Age design practices. But using this methodology, which we developed ad hoc, we were actually able to create something which worked for the customer and solved the problem. And I'm quite proud of that. Hopefully there's some time for questions now. If not, feel free to contact me anytime. You see my email address below. Okay, thank you very much. Thank you for your attention.
Hello, thank you. I got one question for Elchanan. So you obviously applied this technique to an old design, but could you apply it to some sort of C model and show it equivalent to RTL, something like that?
It would depend on what type of clocking, synchronous, whatnots were applied to the C model. I mean, this original design was something which actually did work in the lab. I mean, it was rather, I don't want to use the word pathetic, but I don't have a choice. There were many features that worked only because of bad race conditions and other things which they honed down and somehow managed to get it to work. So it was an original working design. For this C model, you would have to know that there was something in it that really worked. You know, that the implied clocking or the implied cycle delays or whatnot of the C model actually were something that would work in the end. Because we're not comparing to any functional measure other than we presume the first one worked, so the second one should work too. If we don't know that the first one has actually worked anywhere, then we haven't achieved anything.
Okay. Understand. Any questions from the audience? Okay, I think we're going to go into our coffee break now, then, Elchanan. So thank you very much for your talk.
Thank you.